Hi. Yep.
Okay,
Able to look it up. Thank you.
we're going to talk about ionospheric layers, critical angle, frequency, scatter, and NVIS. The ionosphere ranges from 50 to 400 miles above the Earth's surface. I haven't tried to compare because a lot of times they'll represent it in kilometers, and I don't know if those kilometer things were equivalent to the miles or not. It's basically made up of three layers: the D layer, the E layer, and the F layer. And the radiation we're getting from the sun ionizes the uh, oxygen and nitrogen and any other gases in the atmosphere and creates free electrons and positive ions, which are atoms missing an electron. And that's what causes the refraction or the reflection of the electromagnetic waves. So the more the sun sends out radiation in case of the solar wind and X-rays, things like that, the higher the ionization. And the F layer, which is the highest one, receives the most radiation, but it's also a thinner atmosphere, so there's less atoms there or molecules for it to radiate. So some of them come down and hit the E layer, and then a smaller amount manages to get down to the D layer, and then some of it even hits the Earth, and why you get a sunburn from the ultraviolet rays that are making it all the way down. You have the D layer is much denser, so that's why it absorbs more, but it's getting less radiation. So it doesn't, because of it absorbs more than it reflects or refracts. It's not very good for propagation. With the F2 layer at the top, you can get up to 2,500 miles in one hop. So it only takes 3 or 4 hops to get halfway around the world. And the F layer during the daytime kind of splits because you get so much ionization on the upper part of it. It normally rises to a little higher altitude and splits away from the F1 layer. So you see that demarcation between the two, and it disappears at night and tends to get a little thinner at night. This one shows the different layers, the F2, F1, E, and D, and how radio waves from over here in the, which would be the gray line between day and night, is reflecting up off of the F1 layer and back over here to a different point. So you can get about 2,500 miles that way. Showing the D layer totally, or almost totally disappearing at night, whereas they're absorbing low frequency stuff in the daytime. The E layer gets less at night, so it's not as good at the VHF propagation as it is during the daytime. And the F layers are combining back into a single thinner layer at night. So the F are the highest region, 2 layers, F1 and F2. The F2 is where you get the 2,500 miles in a single hop, or up to that, depends on conditions. And it collapses at night to a single layer, and you get a little less than 2,500 miles because it's typically not as high at night. So why is skip propagation via the F2 region longer than that via other ionospheric regions like F1 or E?
Higher.
It's higher. So in this one, it's showing you above the muff, so it's going straight through. And then down here, you're below the muff, and you're getting refracted off of the F2 layer, so you're getting the farthest distance. In some cases, you could get refraction off of the F layer, the F1 layer, excuse me, not quite as far. And the E layer is going to give you even less hop. What's the approximate maximum distance along the Earth's surface normally covered in one hop using the F2 region? 2,500 miles. Okay, the E layer, where we have what's called sporadic E, it's not very reliable. That's why they call it sporadic. But you can get refraction off of the E layer, and it's up to about 1,200 miles because it's just not as high as the F layer. What is the approximate maximum distance along the Earth's surface normally covered in one hop using the E region? About half, 1,200 miles. And apparently that's at VHF, right? Now, what happens at UHF, like 70 centimeters? Does that pass through?
UHF sometimes work, but most of the time, no.
Okay. So it's mostly 2 meters.
It's 6 meters.
And 6 meters. The D layer is the lowest ionospheric layer. It has the most absorption because it's got a lot more molecules, atoms in it, closest to the Earth. Anything below 10 megahertz is normally totally absorbed during the daytime. It doesn't absorb at nighttime because it disappears. So at night, you can do 40 through 160. Difficult during the day, if not impossible.
40 works sometimes.
Which ionospheric layer is closest to the surface of the Earth?
Oh. Layer.
Yeah, what happened to A, B, and C? What are those?
They don't affect politics.
Right.
They got wrapped up in the troposphere.
Yeah, there you go. And we don't talk about the troposphere because it doesn't do anything for us. Which ionospheric region is the most absorbent of signals below 10 megahertz during daylight hours?
The
D region. Question?
No.
Oh. Why is long distance communications on the 40, 60, 80, and 160 meter bands more difficult during the day?
That old thing.
Yeah, that old D layer. It's just useless. Critical angle. In addition to the muff, or like the critical frequency, you have a critical angle, and it's the highest takeoff angle that will return a radio wave to Earth under specific conditions. It's kind of like light reflecting off of a mirror or glass surface. There's a critical angle, and below that angle, it reflects. Above that angle, it doesn't. Same thing with radio waves. If you have a higher too high of a takeoff angle, okay, it's not going to refract. It might get bent a little bit, but it's going to make it all the way through the ionosphere. So the key is that takeoff angles less than the critical angle are refracted. And that's one of the reasons why you care about the height of your antenna, which affects the takeoff angle of your radiation pattern. You want that as low as possible to get the maximum hop. If you're trying to do DX. If you're trying to get the guy down the street, then you better find something else because propagation isn't going to do it. What does the term critical angle mean as used in radio wave propagation?
Highest angle takeoff.
Right. Critical frequency. So for any given angle, there's a critical frequency. So if you're operating at, say, the critical angle, then there will be some frequency above which it will not refract. It's kind of like the way that they measure the muff. Except in this case, it depends on your incident angle. The frequency will change depending on the angle of incidence or your takeoff angle. So if you have a frequency less than the critical frequency, you're going to get the refraction. So it means that your critical angle and your critical frequency are both below the maximum, and you'll get the refraction. Otherwise, it's going to pass through the atmosphere. What is meant by the term critical frequency at a given incident angle?
Highest frequency refracted back to Earth.
Right. For a given angle. Scatter propagation. When you send out a signal, in addition to some refraction, you can get scattering in all different directions. You know, just like when they do radar to, paint a plane or a missile, you get scattering back. Some of it comes directly back. That's what they actually see. Radio waves are the same way, and they can scatter in all different directions, in addition to either passing through the ionosphere or being refracted back. So you can have both. Normally, the scattering is very low signal, and it's erratic. It's not dependable. So if you're getting it, you're getting a weak, fluttering, distorted signal. Because it goes to different angles. You could have multipath. You could actually get it from several different scattering angles back to a receiver. One thing it does allow you to do is receive a signal in the skip zone. So when you're propagating and refracting, your 2,500 miles, let's say, well, that space between where you are and the 2,500 miles away where it's coming back to the Earth, nobody's going to hear that signal. With scattering, people in that skip zone can possibly pick you up. It's also good if you're in a mountainous region where you couldn't do line of sight and you can't do propagation, but with scattering, you could actually get somebody in a valley on the other side of this hill. There's one kind of showing all the different sort of scattering things you can get on its path up through the ionosphere. Huh?
I knew we were going to get down to the troposphere.
Yeah. And we don't talk about the ducting in this one. That's a technician exam is ducting. But it's part of this same chart, so I couldn't separate it. This one's a little more confusing, but it's trying to show where you're transmitting at sort of different angles, and you've got scattering going in these different directions. So some of it's coming straight back, called backscatter. Some of it's forward scatter, so you're coming over here. Some of it's going straight through. You have all those possibilities going on. It's not the best diagram, but it's the only one I found. What type of propagation allows signals to be heard in the transmitting station's skip zone? Why are HF scatter signals in the skip zone usually weak? Right. You only get a small part of the signal reflected or scattered. What is a characteristic of HF scatter? Yeah, fluttering. What makes HF scatter signals often sound distorted? Right. Sort of a multipath effect. NVIS. Here you go, Byron. NVIS. Near vertical incidence skywave propagation, which means your takeoff angle is almost vertical. So you're reflecting signals back down at very high angles. So it includes 90?
Yeah.
Yeah. Well, depending on your antenna. And
only one doctor members.
Only one doctor.
Only one doctor members.
Okay. So you get very short distance propagation with NVIS. And also that's another way to get the guy on the other side of the mountain. And it says sometimes the signal's reflected back. I guess it's not always reflected back, right? Depends on the conditions of the ionosphere.
Often a lot. Yeah. And what you're using.
Right. This is a typical NVIS antenna set up with the dipole low to the ground. It looks like they're like 7 feet. And this one shows, transmitting and all the different sort of backscatter reflections. So you could, if you were in the mountains, you could get into all these valleys. And they showing about a 200-mile radius, which I guess is typical.
Yeah, doctrine of this is 250 to 300 kilometers.
Okay. What's that in miles? I don't remember.
Yeah, 150, 200 miles.
Okay. I guess our chart's about right then.
That's at the very low rate. That's a little bit over 300 kilometers.
What is near vertical incidence skywave or NVIS propagation?
Short distance.
High elevation angles. All right.